So my name is Jubal Patel, and I'm the co-founder of Leap Labs. I'm going to tell you a little bit about what we do in interpretability and why we're focused on it. So machine learning has always been a bit of a dark art, and interpretability even more so. It's not up to the task of evaluating today's state-of-the-art models, much less the exponentially more powerful and complex models of the future. Without better interpretability, the ML utopia will never be realized. So at Leap, we take a nuanced, scalable approach. We treat the model like a true black box. We don't care about the complexity, size, or architecture of the model. And this gives us the flexibility to evaluate any model today or in the future. I'm going to focus on image classification since the theme of this event is computer vision, and that's what our existing product provides. But this method is applicable to all modalities, and LLM functionality will be released in the next month or two, so keep an eye out for that. So how does Leap work? So you have your traditional image classification, right? Give the model an input, runs inference, and it gives you the classification, if it's trained very well, as breakfast burrito, keeping with the theme of the night. So what Leap does is we simply run this process backwards. So we start with the target classification, breakfast burrito, and our algorithm generates what this model has learned is a prototypical example, or image in this case, of what a breakfast burrito is. And it comes up with a prototype that looks something like this. Now this looks quite obscure, but after you look at these for a while, they become easier to understand. So if you can see here, you can see a very clear wheat tortilla as the majority of the image in a burrito shape, as well as some beans here in the bottom of the burrito, which makes me think that there might be some beans in some of the training data that the model used to learn the classification breakfast burrito. So what does this look like in practice? All right, so I'm not going to run this code here because we all know how live demos go. But all of this is run locally. You do not have to send any of your proprietary data or models to us. You simply pip install the Leap library. You specify which model that you're evaluating. Here we actually are using not this Torch Vision ResNet 18, but a food identification model pulled from Hugging Face, but you can use it on any model you have locally on your machine. Put in my Leap API key so that it will spin up in my dashboard, and specify which classes you would like to generate prototypes for. And it looks something like this. So it's an iterative process. So what you can do is you can actually watch the prototypes as they come in, which is kind of fun. So here I've generated prototypes for ice cream, hamburger, pancakes, waffles, and baklava right at the end. So we've got some pretty nice prototypes here, actually. We got some ice cream shapes in the first one, a hamburger, there's some fries inside the burger, which is a little weird. Models learn weird things. Some pancakes and waffles here that look pretty nice. We have a selection of waffles. And the baklava looks pretty nice as well. Now notice that in the pancakes and waffles, there are berries present. So this model has learned that berries are an important part of pancakes, and maybe a strawberry, raspberry, or some other kind of berries on the waffles over here. So keep that in mind. Now that we have these prototypes, we can measure how likely these classes are to get confused with each other by the model through something called entanglement. And I'm going to show you what that looks like down here in our entanglement chart. So what is entanglement? It's the level of feature overlap between different classes as depicted here. A positive entanglement indicates a potential of misclassification between the target class and other classes the model knows. The target classes are depicted here at the bottom of the chart, and we'll stick with our pancakes and waffles example. So if you look at these bars here, these are the other classes and their level of entanglement with the target class. So the most entangled classes of pancakes is French toast and waffles. So let's say I want to disentangle these features. I want to reduce this score and the likelihood that they might get confused with each other. But I need to know exactly what features overlap with the waffles. How do I find out? So we do this by isolating which features of the pancake prototype overlap with the French toast and waffles classes. And we can look at this up here in our prototype isolation. So for pancakes here, Leap automatically does this with the given class and the two next highest entangled class prototypes. So if we play this through, it will isolate the features that lead to the original classification as well as the other two next most likely classifications. And if you notice, the edge of the pancakes are a major factor in these classifications, but also the berries, these blueberries, pop up again in French toast and waffles. Now, I didn't generate a prototype of French toast, but I bet if we did, it would have berries in it. These berries are throwing our model off. And from this analysis, I can hypothesize that if I augmented the data and retrained it with images of pancakes, waffles, and French toast without berries, it can eliminate the spurious correlation and the entanglement between these classes. Another way I can better understand what my model has learned about these classes is by isolating features used to classify a single input. So here at the top, I've chosen a nice image of frozen yogurt. And now we can see exactly which features lead to the frozen yogurt classification. Now, the next likely class is ice cream, which makes sense, frozen yogurt and ice cream. But the last one is waffles. That's a little strange. Can anyone give me an idea of why this model might classify this image as waffles? Interesting guess. Let's see. And sure enough, it is the berries. To be fair, there's also a little bit of the waffle cone in the background, which makes sense. But I'm hoping this gives you an idea of how you can get a more holistic evaluation of your model before you put it into deployment in a way that a validation set's never going to give you, and deploy it with more confidence and avoid failure modes in deployment. So that's enough for me.